So it's Friday of week 9. This is you see the light at the end of the tunnel, and it's week 9 of spring quarter. So just one more week and then a few finals, and that'll be it. Um, so we'll do this. We'll wrap up chapter 9 today. And then next week we'll spend most of that time in review, kind of just covering all of the finer points, make sure we got all of this conceptual stuff down, I hope. And then and that'll be it. I'll post a practice final and along with the a formula sheet. So I will so as part of the final exam you'll get a formula sheet with kind of like on the quiz that you had all of those formulas and equations. It'll be that for all of, well, you'll see, okay? It'll be for the hypothesis tests and confidence intervals for proportions and whatever, okay? So so it should be easy, but I don't know, okay. All right, let's wrap up chapter 9. So we've got confidence intervals. For the quantity mu1 minus mu2 based on 2 samples. Okay, and so here we are making a confidence interval. We make a confidence interval for the quantity mu1 minus mu2. So we are looking at, what is the difference between the average whatever of population 1 and the average whatever of population 2. We are not actually we are not making a confidence interval for mu1 and a separate confidence interval for mu2. Okay, we're looking at the quantity mu1 and mu2. Okay, and so to so an example of this is we might ask, what is the difference between the average price of, we'll say, regular gasoline, and this will be dollars per gallon, and the average price. What is the difference between the average price of regular gasoline and the average price of premium gasoline? Okay, and so the resulting interval may be something like I don't know, 16 cents to 26 or something like that, okay? And the interpretation of this interval would be something like, I am 95% confident that the average price of premium gas is between, basically 16 cents and 24 cents more per gallon than the average price of regular gas. Okay. Does this kind of make sense? What's going on? So again, we're not creating a confidence interval for the average price of regular and a separate confidence interval for the average price of premium. What we're doing is we are just looking at the quantity mu1 minus mu2, which would be the difference between the average regular price and the average premium price. And we're asking, what are plausible values for the difference between mu1 and mu2? Okay, and so we get something like this. Okay, so we'll come up with the the equation for developing something like this. Okay. So we're going to make a confidence interval for mu1 minus mu2, the quantity mu1 minus mu2. Okay. So in the middle of our confidence interval, we would put what? Our best guess for mu1 minus mu2 based on our data. And so what would that be? What is our best guess for that quantity mu1 minus mu2? Yeah, x bar 1 minus x bar 2. This would go into the middle of our interval. This serves as our best guess for what that might be. Okay, and then we would go plus or minus the margin of error, which is always going to be our critical value, times our standard error. Okay, so the critical value will be t star, and our standard error will be the square root of s1 squared over n1. It's just a little bit of an ugly formula, and we can't really do anything about that, but it's not so terrible either. So s1 squared over n1 plus s2 squared over n2. Okay. The t, selection of t, depends on the confidence level and degrees of freedom. Okay, and so our degrees of freedom we will use also n minus 1. Okay, but we have two n's. Okay, so use the smaller of n1 and n2. Okay, and this is kind of just like quote, playing it safe with the degrees of freedom. So depending on, so the truth is that the actual degrees of freedom for something like this is rather complicated. There's this kind of complicated formula or complicated method to try to figure out the degrees of freedom when you are combining, when you're trying to mix together variances from two different populations, and it's actually quite messy. And so, for an intro class, we just come up with these simple approximations. And so our textbook says use n minus 1 using the smaller n, and that's kind of like the quote safest approximation method. Other textbooks might say do n1 plus n2 minus 2, and that would be kind of like the most liberal of degrees of freedom. That would and the true number of degrees of freedom is almost always between those two extreme bounds, where n minus 1 is kind of the fewest degrees of freedom that you could possibly have, and n1 plus n2 minus 2 would be kind of like the most degrees of freedom that you could possibly have. And the truth is that the actual degrees of freedom is probably somewhere in between, but it's kind of hard to determine, so we just say use this, okay? Okay, so I hope you have this down, and maybe I'll copy this onto the next page here, and we'll do an example. So shrink this down. X bar 1 plus x bar 2 minus okay, so let's say we are going to make a confidence interval. So you know, is there a difference between the average weight of apples and the average weight of oranges? This is a very important question. Okay, and so so let's say you get a random sample of 10 apples. Okay, and we'll say the mean weight in the sample. So I'm not sure how you got a random sample of 10 apples, but somehow you did. The mean weight in the sample is, we'll say 105 grams. And the standard deviation is 15 grams. I'm making that up, okay? Don't be upset if these numbers are off, okay? I did Google, like, what's the average weight of an apple and the average weight of an orange, so they're at least in the ballpark. Okay, and then we get a random sample, but I don't know where Google got its numbers, the internet. Random sample of 15 apples, not apples, oranges. Apples and oranges. The mean weight of the sample is 130 grams, and we'll say the standard deviation is 20 grams. Okay, so we'll say make a 95% confidence interval and find the lower bound. We'll make this a clicker question. I've got to figure out some numbers myself. So give me a second here. let me, sorry, get this clicker thing going. You may discuss with your neighbors if need be. Do they still bring puppies to the library during 10th week, or is it, when is it? Finals week, 10th week? They give out free massages. I want to see the puppies. Okay, how are we doing? Are we not getting this? I don't think I think I did this. I hope I did this right. Okay, we'll just say maybe, I don't know, 20 more seconds. Oops. Okay, I'm going to hit stop here, so if you haven't clicked, make sure you've clicked. Okay, so, you know, we just have to arbitrarily label one of these to be sample 1 and the other one to be sample 2. Okay, so, you know, I just did the first one to be sample 1 and the second one will be sample 2. And I'm going to just go through and identify each of these numbers. So the apples, 10 apples will be N1, the 105 will be X bar 1, and then the 15 will be S1. Okay? And then over here I've got 15 oranges, that will be N2, 130 will be X bar 2, and 20 will be S2. Okay, so I've got N1, X bar 1, and S1, and N2, X bar 2, and S2. And then what do I have? I got 10, 105, 15, 15, 130, and 20. Okay? If you find yourself making silly mistakes like getting numbers mixed up and stuff, I would recommend just taking like one extra minute to just write down, not even an extra minute, just write down all of the numbers as they are correctly identified, okay? And then that way when you plug them into the formula, you know, x bar 1 minus x bar 2 plus or minus t star times whatever, you don't, the risk of you making a dumb mistake is reduced, okay? It's impossible to eliminate the risk of silly mistakes, but doing stuff like this can help. So x bar 1, we do 105 minus 130 plus or minus. Okay, so looking up our t star will have 9 degrees of freedom, right? N minus 1, and so between 10 and 15, 10 is the smaller number, so we got 9 degrees of freedom, 95% confidence, so the number I'm going to use at 9 degrees of freedom and 95% confidence is 2.262. Oops, something happened. Okay, so t star is 2.262, so I got this times 2.262, and then plugging in all of this, I got 15 squared over 10 plus 20 squared over 15. Okay, let me copy this onto the next slide just because it's getting messy here. Okay, so my resulting number, I've got negative 25 plus or minus 2.262 times, I think, like 7.01 or something like that. And then so here I got negative 25 plus or minus, I think I got 15.9, is that right? 15.9, okay. And then so my lower bound ended up being negative 40.9. And then the upper bound would be negative 9.1, I believe. Okay. So our correct answer choice, and I think a lot of you guys got it, is answer choice C. Okay. And so this is our resulting confidence interval. So negative 25, I'm pretty sure negative 25 plus 15.9. Yeah, it's negative 9.1, okay? So if this is my resulting confidence interval, I would say something like, I am 95% confident that the mean weight of apples is between, I'm going to write 9.1 grams and 40.9 grams less, because it's negative, right? Less than the mean weight of oranges. Okay? And of course, when I'm talking about apples, I'm talking about the entire population of apples and the entire population of oranges. Okay, so these are about the entire population of apples and oranges. You know, so navel oranges don't have, well, navel oranges, they're kind of funny. It's named a navel orange because it kind of looks like a belly button, and then and they don't have seeds, and they can all be genetically traced back to basically one original navel orange mutant tree. Okay, because you know how do you make orange offspring without seeds, right? So anyway, I just said oranges here. Okay, All right, so let me ask you a question based on this. So we'll say, does our data do our data and the resulting confidence interval provide evidence that there is a difference between the mean weight of apples and oranges? I guess the mean weights of apples and oranges. So do our data and the resulting confidence interval provide evidence that there's a difference between the mean weights of apples and oranges? So your answer choices are yes or no. Okay. All right, get your clicks in, yes or no. Just click something. All right, I'm gonna hit stop here. And the answer is yes. Okay, so that is correct. Okay, so does it provide evidence that there is a difference between the mean weights of apples and oranges? Our answer is yes, because if we look at our interval, our entire interval is negative. Okay, 0 is not inside the interval. Okay, and so this is going to provide evidence that the average weight of apples is less than the average weight of oranges. Okay. Provides evidence average weight of apples is less than average or mean weight of oranges. Okay. On the other hand, if you get an interval with 0 inside of it, then that means 0 would be a plausible value for the difference mu1 minus mu2. And you would not have evidence of a difference. Okay, so if the interval contains 0, then that means 0 is a plausible value for the quantity mu1 minus mu2. Okay, and so we do not have evidence there's a difference between mu1 and mu2. Okay? However, you still cannot say that we have evidence that there is no difference, right? So all we can say is that the values inside the interval are plausible. So we can't eliminate these choices. And we can say we have evidence against stuff outside of the interval. But we cannot say that we have evidence that the difference is equal to any of these particular values. Okay? You know, so I mean, so here's a silly example. You know, what is the difference between the, I don't know, mean salary of lawyers and the mean salary of doctors, or we'll say physicians? Okay, and then, well, okay, so first of all, this could, you would probably need large samples, because as I'm thinking about this, the salaries of lawyers and doctors or physicians will not be normally distributed. Okay, it'll probably be heavily right skewed, because you do have some high profile lawyers making millions of dollars. Same thing with doctors and, you know, surgeon specialists and stuff like that. So, so it will be right skewed, and so, you know, maybe we would run into problems. But let's just assume we could apply the central limit theorem and we get the resulting confidence interval 95% is goes, let's say, negative 32,000 to, I don't know, 64,000 or something like that. Okay, so we would say, so here, because 0 is a plausible, is inside the interval, okay, we would say, you know, we do not have evidence that there is a difference between the mean salaries of lawyers and doctors. Okay. If we gathered more data, perhaps we would end up getting an interval that doesn't contain 0 and provides evidence. But at this point, with the data that we have and the interval that contains 0, we don't have evidence that there's a difference. Okay, but with more data, we might have evidence. But right now, we don't. This is okay? Okay. And then, so lastly, we have hypothesis tests for mu1 and mu2. Okay, and it's very, very similar. I know we only have a few minutes, like 10 minutes or 12 minutes left in the class, but this the process for hypothesis tests of mu1 and mu2 is very similar for the hypothesis test process for P1 and P2, except it's just now mu. You're dealing with means rather than proportions. So I feel like you guys will get it just fine. Okay. So step 1, we're going to make our hypotheses. Okay. So if you recall, what was the null hypothesis when we had P1 and P2? The null hypothesis was that P1 and P2 were equal to each other, okay? In this case, we're going to just say the null hypothesis is that mu1 and mu2 are equal to each other, okay? Or conversely, we could also have mu1 minus mu2 equal to 0. Okay, that's also a fair way to write the null hypothesis. And then the alternative would be identical to the null hypothesis, except we replace the equal sign with something else. So we have this, or this, or this, right? So greater than, or less than, or not equal to. Any of these are the null hypotheses. Step 2 is our preparation step, where we check check conditions, and then we determine or select alpha. Okay, we'll do our calculations. As far as calculations go, same process. Find the standard error. This is the same standard error that appeared in our confidence interval. And you get your test statistic t, okay, which is always the reality versus the expectation. So what we observe is the difference between x bar 1 and x bar 2. The expectation is that we would get a difference of 0. But subtracting off 0 is basically does nothing. So I'm just going to have x bar 1 minus x bar 2 divided by our standard error. And then lastly, we would look up t in the table to get a p-value. Is that good? Okay, and then once you get your p-value, you make your conclusion. And so based on the p-value, if the p-value is greater than alpha, do not reject the null hypothesis. And if the p-value is less than alpha, reject the null hypothesis. So that is always the same. And so, you know, because this process is, in my opinion, so similar to everything else, I feel like I could just kind of leave this here and you guys will get it. So maybe just with our last few minutes, we'll try a imagined scenario, and I think and the question will be really part step 3C and making a conclusion, because I figure you guys know how to plug numbers into an equation and get stuff. Okay, so we will say, you know, let's say the alternative hypothesis is mu1 is not equal to mu2, and then we'll say n1 is 12 and n2 is 15, and you got x bar 1 and s1 and x bar 2 and s2, but I don't know what those numbers are. Let's just say you did the math and your resulting test statistic ends up being negative 2.51. Okay, so then, you know, figure out your p-value, and the ultimate question here is, based on your results, what decision do you make regarding the null hypothesis? Okay, and so your answer choices are reject the null, do not reject the null. Or can't tell. Okay, so your null hypothesis will be mu1 is equal to mu2. The alternative is mu1 is greater than, or not equal to mu2, and your test statistic is this. Oh, sorry. Let me fire up the clicker box so you can click your answer for the for this thing. All right, so we'll say just a few more seconds to get your clicks in, make your decision. Okay, so click, click. I'm gonna hit stop here. Okay. All right, so let's take a look. So our test statistic is negative 2.51. With the alternative hypothesis being a not equal sign, we're just going to ignore the negative sign. And we're going to have how many degrees of freedom? We have 11 degrees of freedom, right? So degrees of freedom is equal to n minus 1, 12 minus 1. Using the smaller n, we have 11 degrees of freedom. Okay, so 11 degrees of freedom. I'm going to look up 2.5. Okay, 2.5 is in between the column 2.2 and the column 2.718, right? Okay, and so that means our corresponding tail is going to be between 0.025 and 0.010. Okay, so the tail is between 0.025 and 0.01. Okay, with the alternative having a not equal sign, so HA has a not equal sign, our resulting p-value will be double the tail. So the p-value is between 0.05 and 0.02. Okay. As far as this goes, alpha was not provided, so we're going to default to using alpha equal to 0.05. Okay? So if alpha is not given in the problem, you default to using alpha equal to 5%. Okay? And so we're going to compare the p-value to alpha. Okay? So our p-value, we don't know exactly what it is, but we do know that it is for sure between 0.05, and 0.02, okay? And we know it's not going to be equal to 0.05 because it's not equal to 2.201, and it's not going to be equal to 0.02 because our test statistic is not equal to 2.718. So we know that it's between these two values. So whatever our p-value is, we do know that it is less than 0.05. We do know that it's less than alpha. So that would lead us to reject the null hypothesis. Okay, that's it. We'll see you guys on Monday. Have a good weekend.